Hey everyone, welcome to this explainer. If you love figuring out how the world around us is actually built, well, you are definitely in the right place. Today we're exploring a fascinating, completely invisible world of engineering. We're talking about the hidden structural shield that keeps modern buildings, and, the people inside them, safe during earthquakes. We're going to dive into the meticulous, high-stakes science of seismic bracing for MEP systems. And MEP, by the way, just stands for mechanical, electrical, and plumbing. All right, let's jump right into this. I want you to do something for just a second. Literally, just look up. Take a look at the ceiling above you right now. Most of the time, we take that clean, flat surface completely for granted, right? We just assume everything behind it is resting quietly. But I want to totally shift your perspective today. What actually happens to all that heavy infrastructure hiding directly above that ceiling when the Earth suddenly decides to move? Think about it. When you have massive pipes, bulky ducts, and cable trays suspended in the air weighing thousands of pounds, a seismic event turns all that static weight into a massive, highly dynamic hazard. And this brilliantly illustrates exactly why we have to completely rethink how things are held up. So on one side, we have your normal gravity hangers. Their entire job is super simple. Just carry the downward gravity load. They just hold weight up against the pull of the Earth. But look at the other side. Seismic motion introduces these violent new forces. It causes lateral sway, which is moving violently side to side, and longitudinal shift, jerking forward and backward. If you're only relying on a hanger designed for downward gravity, those violent side-to-side and front-to-back movements lead straight to catastrophic connection failure. Basically, gravity hangers become a dangerous liability when the ground moves. So how do we actually solve this? Well, here is our roadmap for today. Number 1, the hidden seismic threat. Number 2, 3 unique restraint problems. 3, layout and component selection. And finally, number 4, installation QA before closure. All right, let's get into section 1, the hidden seismic threat. The fix for this threat is what engineers call seismic restraint. By definition, this is the engineered framework you absolutely need to stop that lateral sway and longitudinal shift when normal hangers just can't cut it. And honestly, when you realize that thousands of minor earthquakes happen globally every single day, keeping these systems locked down is absolutely vital. It's not just about, slapping on stronger wires or thicker rods. It is a highly specific engineered geometry. It's designed to absorb and redirect the violent kinetic energy of an earthquake. The whole goal is to essentially lock those heavy overhead systems right into the structural skeleton of the building itself. You want them to ride out the earthquake as one unified structure, rather than swinging around like some massive destructive pendulum. Moving right along to section 2, 3 unique restraint problems. Think about the crazy diversity of the systems hiding in just a single ceiling corridor. We've got pipes carrying water or gas, huge air ducts managing the climate, and heavy cable trays routing massive amounts of electrical power and data. They all share the exact same narrow corridor. They often share the same foundational strut channels, and even the same anchors drilled right into the concrete. But here's the wild part. Because of their different shapes, materials, and internal dynamics, restraining a pipe, restraining a duct, and restraining a cable tray actually represent 3 completely different engineering puzzles. Each one demands a totally different, highly specialized clamp interface to safely secure it against those seismic forces. Okay, section 3, layout and component selection. So the crucial point is this golden rule of the engineering process. You have to start your layout from the restrained object itself and its structural landing point, not by just blindly flipping through a parts catalog. It requires a total shift in thinking. You have to look at the specific pipe, duct, or tray and map its direct path to the strongest, most viable landing point on the building's concrete or steel frame. Literally, only after you've mapped out that physical spatial relationship in the real world do you even begin to think about what specific parts you need to bridge that gap. Once you have that layout mapped, the real meticulous nature of seismic restraint design kicks in with this 6-point component selection checklist. And trust me, every single link in this chain matters. You need the right strut to form the backbone. You need specific clamps tailored for the pipe, duct, or tray interface. You need the right anchors to actually grip the building structure. You need heavy-duty connectors and fasteners to lock the whole shebang together without snapping under sheer stress. And finally, the finish. Because over time, rust or corrosion on these components can secretly eat away at the integrity of your seismic bracing long before an earthquake ever hits. Every single one of these 6 points has to be perfectly selected to make sure the system survives. Which brings us to our final section, section 4, installation QA before closure. I want you to picture this. Imagine you're standing in the room right before the construction crew comes in to permanently seal up that ceiling. You see this number? 7. This represents the incredibly rigorous 7-step installation quality assurance and incoming inspection workflow that absolutely must occur before that ceiling is closed up. Think about it. Once the drywall goes up or those ceiling tiles get locked in, that entire engineered framework becomes completely invisible. If a clamp is loose or an anchor isn't seated right, literally nobody will know until the earth shakes and the system fails. This 7-step QA process is the final line of defense, ensuring that the layout and components we just talked about were actually executed flawlessly. But honestly, you can't execute a perfect QA if your underlying materials are flawed from the start. That is exactly where global manufacturing standards come in, championed by industry players like Shanghai Xinma Busway and Cable Tray Company. They make sure that their cable tray systems, busways, and seismic bracing are backed by strict, globally recognized standards. When you see standards like IEC 61537, NEMA VE1, BSEN 5085, and GB 31251, you are essentially looking at the universal language of structural integrity. These global compliance marks guarantee that the components have been rigorously tested to handle the exact dynamic loads we've been talking about today. And insisting on that level of quality makes perfect sense when you look at where these components are actually deployed. High-stakes environments depend completely on these resilient setups. Take data centers, for example, where a single severed cable tray means millions of dollars in lost information. Or think about rail transit, where a structural failure could literally halt a city's entire transportation network. Consider industrial plants and massive commercial buildings, where thousands of lives are on the line. In these environments, seismic bracing isn't just some boring building code requirement. It is critical, life-saving infrastructure. So the very next time you're sitting in a modern commercial building, maybe a transit hub, or just a busy facility, I want you to do me a favor and look back up. Think about all those massive ducts, water pipes, and heavy cable trays suspended right over your head. Think about the engineered struts, those unique clamps, and the heavy-duty anchors fighting off lateral sway and longitudinal shift every single day. And ask yourself this one question. Did the hidden infrastructure above you pass that 7-step test before the ceiling was permanently closed? Kind of makes you wonder, right? It really is fascinating to think about the invisible structural shield protecting us all the time. Thank you so much for joining me on this explainer, and keep that curiosity strong.